Hey, welcome back to Feedback Control Systems. This is Module 9.3, Improving Steady-State Error and Transient Response. The objectives of this module is to review PID controller design, so this is proportional integral derivative. Then we'll look at a design example for a PID. Then we'll switch into a lag lead compensation, look at one of the examples for the lag lead, and then finally discuss a notch filter for a certain class of systems as a different form of compensator. So first we're going to start with a PID controller design. So in previous modules, we first started with a PI controller, or even before that, a proportional controller, right? A proportional controller, but then we said, let's add some integration. Well, why did we do that? We wanted to achieve a zero steady state error. But what we saw sometimes with a PI controller is that the response may not be as quick as we would like, so we introduced a proportional derivative controller. What we found was we could achieve similar performance in terms of overshoot, but we were able to significantly reduce the settling time, for example, a factor of 2, a factor of 3, stuff like that. So what this is trying to combine all of those features, zero steady state error, faster approach, etc., and come up with a sort of a general controller design, which we're going to call a PID. And so this block diagram, if you look at the previous PI or PD controllers, you'll see the similar elements, right? Here's the PI, here's the derivative part, combining it all together, and here is the equations, again, similar to what we did in previous modules. You'll come up with this, and now notice that we have three terms, K1, K2, K3, and so that was really going to be the focus of what we're going to do in this module. So in terms of a PID controller design, we've outlined a process for you here, and sometimes it's good to follow a recipe or a procedure. That way you can kind of have a good approach and thought process relative to how you're attacking the system. So step one, evaluate the performance of the uncompensated system. So again, what we could do is say you have a compensator. Well, let's actually draw. And this is similar to what we saw in previous modules. Okay? So I might have a reference, R of S, right here. Some feedback, negative feedback typically. And we're going to have our compensator, GC of S, as shown here. That will then feed our plant, which we typically call G of S, shown here. Typically, what we've been doing is having unity gain feedback. Even if we did have some feedback here, what we were able to do is actually take that, roll it in here, and then actually have a unity gain feedback. And then finally out here was our output, C of S. So really, we have a plant. So when I talk about our uncompensated system here, this is really what I'm talking about. What are the open loop poles and zeros, and then maybe varying some gain to get some desired response. Okay. So that's the first step. And so next we can go into the proportional derivative controller. So our GC right here, focus on the proportional derivative part. And what we're going to do there is to meet the desired transient response goals. So we're going to look at zero locations, loop gain as part of that design step. Then we're going to simulate the system. Remember, in previous modules, we showed columns of the uncompensated versus compensated system, and then in the parentheses, remember, it was the actual simulated results. The actual numbers were what we had predicted from theory, but again, a lot of times we are making second-order approximations of third or fourth-order systems, and if they're close enough, again, the simulated response or values in the parentheses were very close, for example, to the predicted one. So we always want to do some simulations to confirm that our approximations were indeed good ones. Step 4, if simulation shows the requirements are not met or not as close as we had hoped, we might need to tweak the design a little bit, so we'll do a little bit of redesign. Once we get something that is satisfactory based on our transient response, now we're going to design our PI controller to achieve a desired steady state error. Okay? So again, the PD controller really there for better transient performance, better settling times, etc. But the PI controller is what gives you that steady state error. For example, drives it to 0. So then from there, once we have that system designed, we can come up with our gains, K1, K2, K3, put it in the compensator realization network that we saw on the previous slide, and then we have our design. Then it's always good to simulate that system to ensure that you have indeed met all the transient and steady state error requirements. And again, if need be, go back and tweak or redesign if the simulation shows that your requirements are not entirely met. So here's a good process, and we're going to follow this process as we walk through a PID controller example. So here is our system. So we can see our G of S term here. And the goal is to design a PID compensator here such that we have 20% overshoot, 0 steady state error when we give a step input here. And what we want to have is that our compensated peak time, T sub P, the peak time where we have the overshoot, we want that to be 2/3 of the value of our uncompensated system. So a lot going on here in the goal, but we'll break that up as we go forward in the design. So step 1, what did we do? We looked at our uncompensated system and kind of figured out where we're at. So our goal is 20% overshoot. That gives us a damping line of 0.456 as shown here. We can look at the open loop poles. We have one at -10. We have one at -6. We have one at -3. We also have a 0 at -8. So those are our open loop poles and zeros. And now what we can do is vary our gain K such that we're on that damping line as desired. And when we do that, our uncompensated dominant pole for a value K of 121.5 is going to be there. And then you can see how the other poles will migrate relative to that. Now, step 2, what we're going to do is we want to reduce that peak time by 2/3. Now, I did not show you the calculation for TP here. We have the table on the next slide as indicated right here, but the approach is going to be similar to what you see right here. So what we'll find on the next slide is the original peak time is just under 0.3 of a second. So 2/3 of that we can substitute here. And here is an equation relating omega d relative to the peak time. So again, what I would like to do, going back into our complex plane here, if we have our dominant pole here, remember that this is our j-axis, and that this term right here, we call that often sigma, and that's going to be negative zeta omega n, that term right there. So when you see sigma, like you do on that slide, that's this relationship on the real axis, and then this term right here we call omega d, which again was our natural frequency times 1 minus. Okay, so these are the two terms, sigma and omega d, relative to where we are with our dominant pole. Okay, so we have a mechanism based on our peak time to find omega d as shown here, and then we have a mechanism to find our sigma value here relative to some geometry as shown here, again based on the angles that we have right there. Okay, so we have the omega d and sigma for step 2. Now we can look at the uncompensated pole zeros, and that compensated pole is when we add up all those angles, we see that we don't have 180 degrees. We're off by about 18.37 degrees. So that information is going to help us relative to designing where our compensator 0 is for our PD controller. Okay, so given the dominant pole locations that we have here, based on the 2/3 TP, we have our pole right there, and then our compensator 0. We know the angle's at plus, so that compensator 0 has to be to the left of that pole as shown there. And then knowing that angle here, we can actually solve for our only unknown, which is our compensator 0, which will come out to be just under 56, negative 56. And again, please note that that is not drawn to scale based on that angle, but just to more show the concept. So we have our compensator 0 location for our PD controller. Okay, so that's our PD controller, and that will then give us our PD controller right here, and then that gives us our desired pole location. We can vary our K, and we'll get a K of about 5.34 to end up on this location right there, right? We've already found the location of that dominant pole based on our TP, and then so by varying K with our root locus, we can actually get to that actual point on that damping line to achieve 20% overshoot. Okay, so we've designed our PD controller. Now, steps 3 and 4, what I would say is we want to do some simulations. So here's our table again, our uncompensated, then our PD compensated system here. So the first thing you'll notice is this TP time, again, down by roughly, TP is a factor of 2/3. And so you'll see that there as the TP for the PD compensated system. And what you'll see first with the uncompensated design is you get a lot of steady state error as shown right there. And you'll see that steady state error is right here. So for the compensated system, you're about 15% lower. But when you're compensated, you actually get a little bit more than half that back relative to steady state error. But also what you achieved is comparing the PD versus the uncompensated here. You actually had, in terms of overshoot, the same overshoot. Okay, same overshoot, 20%, 20%. But it was faster. You actually received your system response faster. So that's where we are. And the PD has reduced both the peak time and the steady state error, but it hasn't made the steady state error 0, which was part of our desire as part of our goal statement. So next, step 5, we want to design our PI controller, and then here's the general form as you see here. So we have a pole now at 0 that we are introducing. And then what we want to do is we have some flexibility in terms of where we put that PI 0 location. So I'm putting it next to the pole at 0 here. So I've chosen -0.5. Again, you can vary that and see differences in the response, but that's where we've chosen it as of right now. So we want to stay on this damping line to get that 20% overshoot again. So given that, we vary our value of K to determine where that intersection occurs. And so here we get a K of 4.6. Okay. Then what we can do relative to adding that integral term into our system is, let's actually clear the ink here for a second. Okay. And what you'll see is the difference between the PD and the PID in terms of the transfer function is really right here. Notice that there is an extra 0 in pole, which is what I'm showing right here. So that's the key difference between these two transfer functions. Now notice the percent overshoot is about the same, 20%. The settling time is a little bit more for the PI, but still better than the uncompensated system. The TP, again, a little bit more than the PD controller, but again, better than the uncompensated system. But notice now your steady state error when we do the simulation for the PI and then wrap it up with the PID controller, you have a 0 steady state error. So now that I wrap it all together, in terms of my poles and zeros, the green here represents the zeros relative to the PID controller. Okay, so we have the S plus 0.50 right here, and then from the previous slide we had the 55.92 for the PD controller. So those are the two zeros. That's the general form of this. We can multiply this out and then solve for our K1, 2, and K3 terms. That's what I am showing here. And then once I have those terms, again, we could go back to our block diagram realization for GC on one of the first slides of this module. And then there's our compensator, our full PID compensator that we could implement for our design. And so with that, we say that this design example is complete, and we have achieved our goals of 0 steady state error and a 20% overshoot. Again, we showed you the response. Our goals have been met through simulation, which we're showing here in the upper left corner. Next, I want to switch into a lag lead compensator design. Similarly to the PID controller design, want to walk you through a design process. Okay? And so first step, same approach that we did for PID, you want to evaluate the performance of just the uncompensated system here, and to determine what improvements could be made, for example, in the transient response. Then you're going to go to your compensator design and focus on the lead compensator to meet the transient response. Again, the desired loop gain, pole locations, settling time, etc. You're going to simulate your system to confirm that the design is adequate, redesign if need be, and then you're going to evaluate the steady state error performance to determine any improvement opportunities. Again, design your lag compensator to achieve that steady state error, simulate the system, and then do a redesign if simulation isn't exactly showing you the results that you desire. So a very similar design approach where, again, for the PID, you're doing the derivative first. Here you're doing the lead first. Then you're going to do the integral term, which is essentially the lag term. And again, you're focusing on first transient, then 0 steady state error, if that's your goal. So jumping into a design, we'll walk you through the steps again. So the goal here is to design a lag lead compensator, 20% overshoot, a 2x reduction of settling time, and a 10x steady state error improvement, for this case with a ramp input. So not a step input, but we're now going to say we have a ramp input, and we want to get 10 times better than the uncompensated system. So a lot going on there again in the goal. We'll walk through this step by step. So step 1, we know the overshoot. Let's immediately draw our damping line as shown there. So there's our damping line. From inspection, we look at the system. We have an open loop pole at 0, one at -6, one at -10. We vary our K, and we'll see that the 0 and -6 come together and then go off axis, and where that intersects that damping line to get 20% overshoot, we can get a value of K. In this case, about 192 is the value of K for our uncompensated system. Okay, and so here again is our table. You'll see as we go through the uncompensated system, we'll do some comparisons as we go forward. Okay, so step 2, we want a 2x reduction in the settling time. So from the table, again, from our simulations, calculations, etc., I didn't walk you through the process, but again, we hopefully have seen this enough where you can independently find TS. Well, so from the table, we see the original settling time is about 2.23 seconds, about 2.25 seconds, and so if we want to reduce that by a factor of 2, then the real part of the pole right here needs to increase by a factor of 2, right? That relationship here for the settling time is that real part along that damping line. So let's just draw that out, okay? Along this damping line. What we need to do is have this still on that damping line, but that real part has to increase by a factor of 2. So our dominant pole will basically go along that as shown. So if I look here relative to this negative zeta omega n as shown here, a factor of 2, the original uncompensated system was at 1.794, so twice that. There is our new real part of the pole. And then in terms of omega d, that's also going to come up as well. And so what we can do for that is we know this part, and then tangent of the angle, we can actually calculate the omega d part up here. So that will increase to about a factor to about 7. So we now know this location, both the real and the imaginary part, and so we're in good shape. So next, what we can do is once we have the original open loop poles, and there were no zeros, but the original open loop poles, and we have this new location for our compensator, we can now pick our compensator 0. Why? Because we know that the sum of those angles, everything has to add up to 180. Here we come up, when we do the calculations, we're about minus 164. So relative to 80, we are at about a 15-degree delta. So that'll help us relative to find our angle relative to that. So when we then look at these two numbers right here, there's our desired location, and we have a 15-degree delta. We can essentially use that to find our compensator pole for our lead network, and then from this geometry we can find that the angle will be, the value of the pole is minus 29.1. Okay, so one comment, I think I just made a slight error here on the slide. So the sum of the uncompensated pole zeros and the compensated zeros is here, and so this ZC really, I believe that should be PC because that's our compensator pole. We had selected, remember as we do our lead design, we have to select a closed loop 0 right here, and we chose one at -6 right here to do a pole 0 cancellation. So I glossed over that part. My apologies for that, but I wanted to back up and address that, and also that this angle right here should be PC because this is our compensator pole angle here of 15 degrees. So sorry about that, and then we can use that to find the compensator pole location as shown there. Given that, we can now, given that, we can sweep our value of K and find a K of just under 2,000 relative to get our compensated dominant pole on that damping line to get our 20% overshoot. Okay, so you'll see the pole 0 cancellation there, and then so. As I walk through this, I have a pretty high gain here associated with that lead compensator. I then do my simulation, and I can compare the uncompensated system here in black versus the lead system that I'm showing here in blue. And what you'll see is the settling time has indeed come down by a factor of 2. 2x reduction was our goal. And again, you can see this again if you look at the table. Visually, it looks the same, like a factor of 2, but here on our table, you can see as well that factor of 2 going down as well. So let's get rid of some ink here. Okay, and again, you can see that with regard to the settling time, again, about a factor of 2. The overshoot remains at about 20%. Okay, so far that the lead compensator looks good. Now what we want to do is design our lag compensator to improve the steady state error. Okay, so this was our original open loop uncompensated system. With the gain of 192.1, okay, and that was this one right here. So that was our open loop uncompensated system that I'm showing right there. So the 192.1 we had found previously, and then once we include our open loop lead compensator, notice that we canceled out that term, and we basically had this other pole, and then the gain went up to just under 2,000. So that's our open loop system with the lead compensator included. And then so now, because we have a ramp input at the reference here, we need to find out what that static error is for that ramp. So we have our system here. Multiply it by S, so you'll see that S and this S cancel, and then we have our S terms go to 0. And then, so what you'll see is I've shown the various KVs, first for the open loop uncompensated system, and then for the open loop lead compensated system here. And then, so to get an improvement, so going from GS to GLC, there was an improvement of about a factor of 2, right? So the KV for just the GS, open loop uncompensated system, 3.21. The KV for the open loop lead compensated system was up to 6.8. So that's a factor of 2.122. That difference, just by going with the lead compensator, gave you that. Now, we want a total of 10x improvement. So we already have 2.12 from the lead. So with the lag, we got to do another 4.7. So when we multiply those two together, we get a total factor of 10. Okay, so we need to do one. So let's pick our pole at 0.01. And when I walk through this, what I'm going to do, based on our new versus old definition with our compensator pole in 0, this is from a previous module when we looked at the static error constants. I'll refer you back to those. But we can come up with our lag compensator. So again, when we pick the pole here, that results in a 0 there for our lag compensator. And so the resultant lag lead compensator is shown. Let's get rid of some ink. Okay, so our resulting compensator is, we have, notice in the denominator, right there, that's what we have here. Okay, that's basically for our lead, and then here's our lag term right there, and then we have our lag 0 right there. So then I just have a value of k that I can change, so that's our lag lead compensator. And then what I can do is, again, vary my value of k to get my desired dominant pole on my 20% damping line that I have here. So notice that I get a value of k, 1971, whereas before with just the lead it was 1977. So essentially the same value of k when I put in my integral compensator. And the reason, if I look at where these are located here, you would expect that value of k would be relatively close. Okay, and then so now what I could do is look at step responses to the ramp inputs. So first, I'm showing the input here, whether I have the uncompensated system in black, which is the lowermost line. The input is the uppermost line here, solid red, and the lead compensated, just the lead compensated here, is this little light blue one in between. And then when I add the lag lead compensated system, just comparing that to the input, you'll see that it matches pretty good. So if we were to do that comparison sort of in the steady state, it's hard to just visualize that has that 10x improvement, which was, again, our goal. So let's just kind of go back. Again, we want a 10x improvement. And when we look at our steady state error, which is right here due to the ramp input, for the uncompensated system, we had an error of 0.312, and then for the lag lead fully compensated system, you can see there that it is indeed a factor of 10 reduction through the design process that we had. Okay, so basically met our goal with, again, maintaining our 20% overshoot when we were to do a step input for that system. Okay. So the final topic I wanted to do in this module is, every once in a while you might get an uncompensated system where you have poles that are right there. So for systems with high frequency vibrations or oscillations, you may get a closed loop response, may be difficult to obtain when your poles are, again, near the j omega axis where you would expect that oscillation, right? So maybe if your plant poles were here, you had some higher frequency poles, etc. So designing this compensator may be difficult, and again, you might get a response here. So a lot of oscillation, a lot of high frequency oscillation. It damps out and eventually goes, but you may not want that high frequency vibration. It may lead to noise or wear out mechanisms, etc. So an approach here, and we're not going to walk you through all the details, but more of a conception is, if you look at the pole 0 plot of a notch filter, I'm going to have two poles and then two complex conjugate zeros here. The goal is to have these two zeros essentially try to get rid of or cancel those as close as possible, and then try to have those sort of dominate. So that's kind of what you can see here is your notch poles over here, your plant poles over here, and then so here is what our root locus is, and we can then vary our gain, etc. So this will be the root locus with the cascaded notch filter. Again, I'm not showing you the transfer function or any of this, but just more of a concept. And what you'll see here is you can get a response without this high frequency oscillation. So there is sort of an approach here that you could take. But again, what you'd have to worry about relative to these plant poles is instead of going here in a very stable, fast direction, that they now go in this direction, which again, depending on the amount of gain, you have to watch out. Even though this looks good, with a little bit more gain, that could go unstable. So you'd have to watch because those poles are again now migrating. They want to trend into the right half plane. So care must be taken, especially you'll have to look at this with regard to sensitivity, etc., just to make sure you're going to be good for the life of your design. Okay, so that'll wrap up this module. If you have any questions on any of this, please don't hesitate to reach out. Thank you.